All right, now that the cylinder block is completed, there are a number of elements that need to be connected to it. So let me just hide some of these parts so we can get a better look. Okay. First off, the original plans called for this Pyrex displacement cylinder to be simply glued into the cylinder block, which I'm sure would work just fine, but my concern is that it's glass. If it breaks, how do I get it out, remove the glue, put another one in? And also, if I ever have to get in here to make any adjustments or anything, I would prefer a mechanism that allows me to make a tight seal and yet be able to remove this glass cylinder and replace it. So what I came up with was this, what I call a cylinder adapter. This is a close-up view of it, and what I've decided to do now this part will fit right into the cylinder block where the original plans would have had the glass tube going directly in. I've milled this and the hole in the cylinder block larger so the cylinder itself can fit inside here. But then what I've done is I'm going to machine out two grooves, inner grooves in here, and fit them with O-rings so that we can just do a nice snug force fit of the cylinder in here. It ought to be airtight. And it allows me to remove it just in case I ever need to. So let's go build that part. All right, I'm working on the cylinder adapter now that's going to have the internal O-rings to hold the glass cylinder. This piece is much longer than the actual piece that we need, but because the vise needs, or the jaw needs a way to hold on to the piece, and I have to machine it from both sides, I had to leave extra stock on each side. One reason is that one of these sides is going to be finished and visible on the part, and when I flip that over, the jaws will mar the finish. So I have to leave either extra on both sides, and then we're going to have to cut off what we don't need. It's frustrating, but it's just part of the process until they invent a force field or something to just hold the piece in the air. So anyway, the first thing I want to do is find Z0, which is the face of the stock. So what I do is I just advance by the way, I have faced both ends of this piece prior to getting started here. So what I'm going to do now is just jog in. I'm just moving in 1,000th at a time, because I just want to kiss the stock. And that's it. So I now set my DRO, and I know that is Z0. And now I'm going to move in X. Again, one increment at a time until I just touch the stem. Okay. So now I can set my DRO. I know that this stock is nominally 1 1/8. So I set my my DRO to 1 1/8. So now the DRO knows, or now the machine controller knows where we are. The next step now is to turn this down until we get it round. I mean truly round, because again this is just as it came from the mill. Okay, so I've just set up a G-code wizard just to remove, what am I taking off? I don't know, like 25 thousandths or something. Just enough to get this, trued up. The machine thinks that it just cut the diameter to 1.1 inches. The actual diameter is 1.10. Close. All right, well, it's within 1,000th of where it needs to be, so it was just blind luck. So now what I'm going to do is modify that wizard. Normally what I would have done, had that not matched, I would have advanced the tool to 1.1, where it left off, and then corrected the DRO to the true measurement that I took off here, but since it's essentially the same measurement, again, this is decorative, it's not, 1,000th isn't going to matter, plus we have to stand it anyway. All right. Okay, that's actually right on. So now I'm going to flip the part around in the chuck and machine the other side of the piece to its dimension. All right, I flipped the part around. I found Z and X the same way I did a moment ago by touching off on here, and now I've got a little program set up to machine the first ½ inch of this down to 0.95. This is the end that's going to be pressed into the cylinder block. So this dimension does have to be right. So the final dimension is 0.925. I'm going down to just 0.95 now, so I can recheck where I am when I get there, and then make any adjustments that are necessary. as I said, what I do now is I'm going to do a G0 to 0.95, which is where the machine thinks we are. I'm going to tell it what we're I'm going to change the DRO to read. That's dead on. So the real proof would be to take the actual cylinder block that we're going to force that into. And yeah, it's there's about, half a thousandth or so of play, which is fine because I'm going to Loctite that in. Now, obviously, this is longer than it needs to be because we want to come flush up to here. But I had to leave it this way because now we have to flip it around again in the chuck and bore all the way through here. And if I didn't leave some extra stock, we'd be boring into the chuck. So, I'll bore, certainly deep enough, for this recess, but not so deep that we hit the chuck. And then later we'll flip the part around 20 more times and remove that extra stock. We have to now drill and then bore this part out so that it can fit what will ultimately become the main cylinder after we cut this down to size. So it's quite a bit of drilling and boring we're going to have to do here. I can drill up to about 3/8 of an inch, and then the rest of it we'll switch over to the boring bore and we'll do that. Not much to it. What I measured here is that this entire piece is 1.5 inches, and I'm only going to go down 1.35 into here because, like I said, we do not want to be, boring into the chuck. Sort of have to heck drill just like we would on the mill. I've drilled the starting hole out to 3/8 of an inch, which, like I said, is the largest drill bit I can use on the lathe. And now I've put my boring bar onto my quick change tool post, I've ensured that the cutting edge is dead on the center line. And I've made some trial cuts and gotten an approximate dimension of how large the hole is. We have quite a ways to go, because right now we're at roughly 0.4, and we've got to go out to 0.866, which is, considerably larger. And in fact, a hole has to be big enough to fit this, glass tube, which is going to be the main cylinder. So anyway, so I've set up again, using the wizards in Mach 3, I've set up a boring routine to start to enlarge this hole. I'm going to go out to 0.8, which is 66 thousandths less than the final size. So once we get out there, we can do some very accurate measuring and then sneak up on the final. But you'll see quite quickly that this boring operation is a whole lot different than what we did on the milling machine, because it can be controlled well, that wasn't expected at all. I have no idea why that just happened. I went back and took another look at the G code, and what it turns out is that I was removing twice as much material as I thought I was. It's the old, are you removing it from the diameter, or are you removing it from the radius? I actually only want to make a 6,000th cut, and I was doing twice that, which is way too much for this machine to handle. So it should proceed much better now. Alright, well, I finished the boring operation out to a diameter that the machine thinks is 0.8. I'm going to see what it really is. Of course, that was just an approximation, because I didn't have a good starting point. But now, right, now it would appear that the actual diameter is 0.789. So now I'm going to bring the X slide into that's where we left off. That's where the machine thinks 0.8 is, which is what we think we just did this to. But what we're measuring in practice is 0.789. So what I'll do is adjust the DRO to match what we really read, 0.789. I know you can't see that I'm doing that, but that's what I just did. And now I will I'll go in and modify the G code. Let's do the first sanity check. Yes, the hole is still too small, but we're very, very close. So, measure it again. Well, it turns out today's lesson, boys and girls, is don't buy cheap tools. This was a really cheap set of boring bores, and that seems to be what the problem is. I switched through a couple of them, and I finally found one that's actually cutting. Anyway, I just took a measurement here, and we are now 15 thousandths shy of the diameter we want to be at. So I'm just going to use MDI commands now and sneak up on that. I'll make a few cuts and measure again, until we get to the diameter we want to be at. Alright, magic. That's just fitting in there exactly the way I want it to. So, a little bit of blind luck. There's still some chatter in there. I am definitely going to buy some new cutting tools before we do the next boring operation in this project. But for now, that is the right size, and the chatter won't matter at all for what we're about to do next. Because what we're going to do next is cut some inner grooves to put some O-rings in to hold that test tube in there nice and tightly. Last night there were a number of issues with the boring setup that were making me crazy, so I did a bunch of research, and the tools I was using were an extremely cheap set, and in fact an entire set of 9 tools costs what one good tool would have cost. So it was a cheap import, and I know that that was part of the problem. But apparently another part of the problem was your setup has to be incredibly rigid when you're doing boring. So I'll have to work more on that in the future, the next time we do some boring. But now what we're going to do is cut a groove for some O-rings that will sit inside this adapter, so that when we press the test tube, which is the cylinder, in there, the O-rings will give it a nice tight seal. At least that's the plan. So first off, this bit, there's a company called Thinbit. You can find them at thinbit.com. I've heard a lot about them from other machinists. They make, well, obviously they specialize in small bits, which is why they're called thin bit. And they can pretty much make anything. They have a very wide selection of the kind of bits you're not going to find in other places, but like this one in particular is a 80 thousandths, which is one of their stock bits, and it's the one I need for the size O-ring I'm using. But if I needed this to be 79 thousandths, I could have ordered one and they would have made it for me. Needless to say, they're not cheap, but from what I've heard, they're well worth the price. So step one here, first of all, if you recall, this is a lot longer than it will be in the final, when we're finished with it. In fact, it only has to be about out to here. So I left plenty of space here, and there were a number of reasons for that, but one of them is it's going to allow me to test making some O-ring grooves in here. And then, we can just part that off and then make the real ones based on what we learned. So that's the plan. What I'm going to do first is figure out how far we have to bring this so it's just touching. Now what I'm going to do is I'm going to disconnect the servo on the cross slide, because this is the kind of operation I just want to do with the hand wheels. My guess, again, I've never done this, but my guess is because this tool is shaped very much like a cutoff blade, that you want to use a relatively low RPM like you would if you were doing a cutoff operation. What I'm going to do is bring the bit in until it just touches. I'm turning the hand wheel here very slowly, just listening for it to touch. Okay, it just touched. So now what I'm going to do is zero the dial on the hand wheel. Now I'm going to put lots of cutting fluid in here, again as though I were doing a cutoff operation. Now the plans call for the the groove to be 50 thousandths deep, which is one full turn of the hand wheel. So I'm going to go nice and slow, listening to what we am watching. You may be able to see the groove starting to form. Okay, that's 50,000, so I'm going to back it out. So now I have this this O-ring. It's 21.5 millimeters inside diameter, which is just a hair smaller than the test tube's OD. Now, I guess in theory, this should somehow snap in here. It's in there now. Let's see how that feels. Sweet. All right, that's perfect. I know you can't tell, but it is an incredibly tight fit. This isn't going anywhere, and I'm sure there's no oil leak, air leak. So my plan is actually to put 2 O-rings in here, just to be absolutely sure that there is no air leak. But now I know that that was the proper depth, for this to work. So I'm glad we did that. All right. I guess what I'm going to do now is flip the part around, fix the, get the final depth on this side. All right, I also bought a new parting tool set up from Thin Bit. It's a little big for this lathe, but it should work just fine. What I do when I'm setting it up, it is critical that the blade be exactly straight with the stock. So what I do, I know this is a nice faced-off end here, so I've just brought the tool right up against it, and now I'll just tighten down the tool post so we're square there. The other thing is you have to have your tool right at dead center, or maybe a hair below it. And I have this this little guide that Stirling sells these, but it's machined such that if your tool bit just fits under there, you're at the center line. So that's exactly it. So that's set. I'm going to bring this right in until it just touches. Set that. That is now my Z0. Alright, let's give this a try. Same as before. Nice slow speed. Lots of fluid. And I'm just going to turn by hand using the hand wheel. Nice. I can tell you already that I really prefer this cut-off tool to what I've been using. First of all, the tools you get from Thinbit are incredibly sharp. You know that the first time they touch metal. The second thing is, it's always annoyed me that when I do a cut-off with a standard cut-off blade, which are ground flat this way, you always have a nub left on the part that comes off. This one is ground at a bit of an angle this way, so that it's cutting the drop-off part first, which gives you, nothing is left behind here, and then you advance the tool in a little bit more, and you get that same nice clean cut on the other side. So this was well worth the investment. I have always stressed over doing cut-offs because I just never felt that I had any control. This feels really nice. So, all right, so next I'm going to measure this again and face it to get it down to so that it sits flush. I can see that there's very little I have to remove, but I want it to sit flush with this edge here. All right, the adapter has now been cut to its final dimensions. I use the parting tool and I cut off the remaining stock that was here. I've got the O-ring cutter back in the tool post, and now I've brought the outer edge of the cutter up to the outside diameter here, or dimension here, and I've set the DRO to 0, and now I'm going to come in 0.169. So I just brought the tool in 0.169 because I want the trailing edge of the tool. The tool is 80 thousandths wide, and I want the trailing edge of the tool 0.89 in here. So now, as we did before, I'm going to find the point where the tool just touches, which is right there. Set my hand wheel to 0. Lots of cutting fluid in here. And now, just as before, I'm going to use the hand wheel and cut in 50 thousandths. Now I'm going to advance in another 100 thousandths. All right, so now I'm set up to cut the groove for the second. Second already. The last thing I want to do, this has obviously a flat edge on it, and I think when we slip the test tube in here, it would look nicer if this were had a radius on it. So what I'm going to do is just use some files. I have a medium file here where I'll start to do the rounding, and then I have a finer one where I'll clean it up. tough to get the right angle here because I'm so close to the chuck. So I should be, rolling this, but just don't want to hit the chuck joints. It's starting to form now. All right, switch to the finer one. All right, that's good. I'll just clean that up with some sandpaper, and we'll be done.